I'm talking about fair representation clustering with several protected classes. This is a joint work with Yury and Ali. In a classical clustering problem such as K-median, we are given n points and we want to cluster them into K clusters. The objective is to minimize the sum of distances of points to their assigned centers. Here, D is the distance metric, capital X is the set of points to cluster, and for each X in capital X, phi of X is the center of the cluster that X is assigned to. In a fair clustering problem, we are given n colored points, and we want to cluster them in a fair way. Here, fairness means that each cluster should contain a certain fraction of points of each color. For instance, if we have 10 red points and 10 blue points to cluster, we may require each cluster to have the same number of red points and blue points. For instance, the clustering on the left is not a fair clustering, while the clustering on the right is a fair clustering. More generally, we might have points X, and each point might come from L disjoint groups. So here we might think of groups as groups of colors. For instance, X1 is the group of red points, X2 is the group of blue points, etc. And we say that the clustering is fair if, for instance, the fraction of red points in each cluster equals the fraction of red points in the population. More generally, we might relax the requirement and to say that the fraction of red points in each clustering is between alpha j and beta j, where alpha j and beta j are usually picked to be numbers that are close to the fraction of red points in the population. So in this work, we studied both the exact fairness and the more relaxed version of fairness, and we want to design approximation algorithms to fair K-median problems. And the motivation for this problem are as follows. So first, different benefits might be associated to each cluster, and we want to balance the proportion of people in each group who receive a certain type of benefits. And secondly, in machine learning, usually clustering may be used as a feature engineering step. So we do not want to introduce bias to the data set or to the feature. For instance, maybe we have data sets that are, some of them are labeled as positive, some of them are negative. And we don't want to create clustering such that some clustering only contain one type of points, but not the other. Or maybe the data set correspond to some information about male, some of the points corresponding to information about female. Also, in this case, we don't want the features, the clustering to only contain male or only contain female, which would make the feature rather biased. So as a feature engineering, we also want to have fair clusters. We also want to produce fair cluster as a new feature. So before giving the result, let me mention some previous works on this problem. So the first paper on fair clustering is in the Fair Clustering Through Fairness paper. And later on, there are some other papers which studies the definition of fairness like proposed in this paper. For instance, later there is a near linear approximation algorithm proposed in scalable fair clustering paper. And in this case, I think there are only 2 colors considered in this paper. And later on, a relaxed version of fairness is proposed in some other papers. For instance, in these 2 papers, they generalize the notion of fairness to the exact fairness to the more general version of fairness that we just described. And later on, there is the paper which gives a constant factor approximation algorithm is fixed parameter tractable. and it uses the technique of core set. Yeah, that are the previous works. That has some of the previous works. It's not exhaustive. So now let's consider our main results. So our first main result deals with the definition of the general notion of fairness. And our result shows that there exists a randomized big O of log K approximation algorithm for fair representation K median problem that runs in n to the big O of L time. And note that in practice, usually K and L are both small compared to n. So in some sense, if K and L are both constant, then our algorithm provides the first constant factor approximation algorithm, which runs in polynomial time. Our second result is on the notion of exact fairness. And in this case, we could speed up the algorithm. So again, our approximation algorithm is a big O of log K approximation algorithm. But the runtime now is Kf to the big O of L times log n plus poly n, where F is the fairness size. And as we will see, F, like in practice, is usually very small compared to n. So we can safely take it to be a constant sometimes, so that the dominating term in this sum is poly n, which is much faster than the previous algorithm. Okay, so that's our second result. And just to consider, so for instance, in this example, the fairness size F is 3. So fairness is usually the smallest set of points. So fairness is a minimal size non-empty set of points that is exactly fair. And we denote the size of a fairlet by F. So for instance, in this case, each fairlet should contain 2 red points and 1 blue point, so that F equals 3. Okay, so now let me describe some main techniques of our work. So to begin with, let me talk about our first result on general notion of fairness. So this takes like several steps. First, we transfer the points to K locations. So what we do is that we first run a vanilla K median algorithm. So this K median algorithm provides the clusterings which are not necessarily fair. And then we we move our points to the K centers. And we move each point to the centers of the clusters that it is assigned to. And now we only have, originally the points might be spread out in n different locations where n is the number of points. But after this step, the points are all located on in K locations. And it can be shown that in this step, we only lose a constant factor. And on the second step, we embed our data to a binary tree metric such that every non-leaf vertex has exactly 2 children. And in this step, we might lose a big O of log K factor. And in the third step, we do a dynamical programming on this tree metric. So the way we do this dynamic programming is that we consider sub-problems on subtrees. So subtrees means that subrooted trees. So we consider, for instance, we consider the root here, and we consider the subtree in this blue box. We solve similar problems on this blue box, and then once we consider the left subproblems, the right subproblems, then we consider the problems on this whole tree. And each subtree, so the idea is that if you want to have a fair clustering, then each subtree might import and export a certain number of points of each color. So what do I mean by imports and exports? So what I mean is that, for instance, let's consider the subproblems on the subtree bounded in this blue box. Then maybe if we just consider using points from this 3 node, so each node contains a certain number of points and possibly 0. And if it might be possible that, say, every point contained in these three nodes are red points. And in this case, it is impossible to produce fair clusterings just using the set of points inside these three nodes. And in this case, what we do is that we need to export some number of red points to outside this blue box, outside this subtree, and import some number of blue points in this subtree so that we can produce a fair clustering inside this subtree. And how do we get dynamical programming? So given the solution to child nodes, we can find a solution to the parents nodes using a recurrent relation. So in this case, let's now assume that the sub-problems on the left subtree and the right subtree are both solved. And now we want to solve the problem to the whole tree. How do we do? So for instance, let's say that we import 5 points to this whole tree here, 5 points to this whole tree. And for simplicity, let's first assume that this root that will not contain any points at the end, which is one of the special case in this work. So, and now we need to export these 5 points either to the left subtree or to the right subtree. And again, note that it is possible that we actually export a negative amount of points to the left subtree, which means that we import 2 points from the left subtree, and then we might give all the 7 points to the right subtree. And note that in the optimal solution, we must import and we must export some number of points to the left subtree and some number of points to the right subtree so that their sum is 5 in this case. And if you already know the answer to the left subtree and to the right subtree, what we can do is we consider all possible combinations of, like, for instance, -2 and 7, -3 and 8, or 2 and 3. We consider all these possible ways to export points to left subtree and right subtree so that their sum is exactly 5. And we know that we just take the minimum. We know that the cost in this case, for instance, if we import 2 points from the left subtree and we export 7 points to the right subtree, then the cost is simply the sum of the cost of the left subtree plus the cost of the right subtree together plus 2 times the distance of this edge plus 7 times the distance of this edge. And in the dynamic programming, we just search for all the possible ways to decompose 5 into 2 numbers, and we take the minimum cost at the end. That's our algorithm. That's our dynamic programming algorithm. And now let me considering the problem of consider the second problem. So we consider exact fairness given in the previous definition, where we need alpha j and beta j to be both equal to each other, and moreover that should be equal to the proportion of points in each proportion of points in the population. And for instance, if x1 is a group of red points, then alpha j and beta j should both equal to the proportion of red points in the population. And the idea of this result is that we first run algorithm from previous work, which gives a clustering that is close to fair, which means that it violates equation 1 a little bit by additive amount. And then we can show that we can do a reassignment algorithm on the result on this clustering to only a small number of points in each cluster. So basically, it can be shown that we only need to run this LDP algorithm to KF many points. This work is funded by DARPA and NSF.